couple of others, the length and the number of x's along the backbone, actually, to predict the cath, so at this level of the classification, cath structure. And we get about 75% accuracy with just these four numbers. We have some competitors, Peter Rohn in Copenhagen, who with 30 real numbers is able to get about 98% success. And we, if we use, never mind all this topological type, we just use the word in x no x along the backbone, we get comparable data to what he does. Namely, we can really predict, namely, the pattern of x's along the backbone with 98% accuracy predicts the h level of this classification in logs. All right, so I did that. I think I don't have time to discuss RNA, so I shan't. Let me just say that some of these same techniques Jorn and I have been recently using to start to classify knotted structures in RNA, which is sort of a new frontier in RNA. New not only for us, but new in the community. And I'm sorry I don't have time to describe that. We'll hear that later. And let me move on to, that's the combinatorial model. The continuum model is sort of staring us in the face. And then let me tell you quickly how we're using it, and then try and give you this definition of protein marginal space. The continuum model, well, we've already discussed that to a pair of peptide units is associated an element of SO3. So the biophysicists, remember we have these conformational angles phi and psi that they like so much to describe the geometry along the backbone. So they have this torus to conveniently describe the local geometry along the backbone. And it's been actually a long-standing problem in the protein community. How can we give a reasonable low-dimensional phase space, for example, for hydrogen bonds? Answer: if there's a hydrogen bond between this peptide unit and this peptide unit, there's an element of SO3, and so we can fix the primary structure, the residue here, the residue here, the residue here, and the residue here, or maybe say three of them if we'd rather, or fix the chemical structure, and look at a distribution on SO3 corresponding to the hydrogen bonds that occur. You see what I mean? We can now go to this PDB and sample it by computing densities on SO3 corresponding to when's there a hydrogen bond if there's this particular pattern of residues. So this we have been doing, and I just wanted to show you, I have a, just, hot off the press. Yeah, here we go. It's down here. I hope. Here is for a three-tuple, one of the residues is called valine, and if you have valine, if three of, so there's a hydrogen bond, and if there's a valine and I don't care what, and a valine and a valine, we've gone to the PDB and sampled. And here is this picture. The way we're plotting this is, of course, an element of SO3 can be given as a quaternion, or let's say as a vector and a rotation about it. So we plot the vector length given by the amount of rotation. So it's good sort of near the origin, and it's not so good far away from the origin. At any rate, here is the density on SO3 in this representation of a valine-valine blank valine hydrogen bond. So I hope you understand. I mean, this data has been sitting in the PDB for 30 years or whatever. I mean, I'm not sure anyway. But this data, this ever-increasing pool of data in the PDB allows one to understand the geometry of hydrogen bonds. And nobody has had a vocabulary for probing this. And now I hope this seems obvious. This seems like obviously a good idea. Towards what end? Well, towards, say, the folding problem, namely, we can, so here's the most primitive thing you can think of. So here's I'm talking about the continuum model, and here's sort of an application of what I just said. An application of the continuum model. Well, remember I mentioned something called molecular dynamics. And you can take the energy, so take the energy E of any, choose your favorite version of molecular dynamics, of any molecular dynamics prediction, protein folding prediction method. Let's call it E. And we're going to take sort of an E, I don't know what you call it, E nu. to be the old energy, and what I'm going to do is regard the data we see as governed by a Boltzmann distribution. So that the probability is, the log of the probability is negatively proportional to the energy. And let's just add that term here. There's a coupling constant we don't know. So there's some positive or negative coupling constant. And to that I sum the log of what we observe. So this is over all, say, the H bonds, or whatever we're studying. There's all sorts of, let me make another point in a minute, but here in this current context, over all H bonds, the log of what we observed conditioned on the data that we see, on that data. And just add this term, the natural thing, say it's a Boltzmann density. Go often with a few proteins, kind of tune alpha to an optimal value, and now do this topologically enhanced, or whatever version of molecular dynamics. It's a very natural idea. And I don't know, Jorn, have you looked at the latest runs? I didn't see it. We got some data back. I'm not sure how good it is yet.
I didn't see it.
If we include just the probability, this Boltzmann probability stuff along the backbone, we do actually quite well. We're able to improve molecular dynamics by, you remember, 30% or something like that. We do, in other words, we run this molecular dynamics, crude, admittedly, in molecular dynamics routine, and we add our term just for the Boltzmann distribution of phi's and psi's along the backbone. What could have been done before? And we get closer to the true structure by about 30%. So there's evidence that this is not a crazy idea. This very primitive notion is not a crazy idea. But let me go a little further and say, okay, it's been this holy grail problem in computational biology to figure out a low-dimensional phase space for hydrogen bonds. But we're not married to hydrogen bonds. Take any sort of interaction of any two peptide units, and there's a density on SO3 for the appearances in the PDB. For example, just spatial proximity. Suppose so we've got this thing and it's folded, and suppose these two peptide units are nearby one another. Well, then there's an element of SO3 relating them, and we can look at the statistics of that as well. So the sort of tertiary structure notion of using these SO3 bags. All right, so there's some notion of the continuum model that we've been studying, and now let me just quickly, in the remaining few minutes, try and define this protein moduli space, because I think at the end of the day, there's actually something sort of beautiful, pure mathematical to say about these ideas. We'll see if you agree. I don't know. It's not. Well, anyway, let me get it on the board. Now. Okay, so here's moduli space. So what I'm going to do is I'm going to contract. This will be convenient. It's going to be some elaboration of the moduli space of SO3 graph connections on a graph. But I'm going to have to allow the graphs to vary because bonds may come and go, for example. And there's going to be an elaboration that includes some notion of strength of the interaction. So anyway, with having said that, here's how I'll proceed. It's convenient to take these, I guess what I just erased, these little models for the peptide units and shrink them to a point. So my model for the backbone now is even more boring than before, let's say. It's just this, where each dot denotes a peptide unit. All right? However, we can recover the hydrogen bonding by putting arrows on the edges, arrows that point from N to O. So I can recover the little, the previous picture by simply putting edges, saying that it goes from H to O. So we add edges for the secondary structure, for the hydrogen bonding along the backbone. And if I go from H to O, it turns out that there are bifurcated hydrogen bonds like this. So a given O occurs in at most one hydrogen bond, but two H's could occur with the same oxygen. You see what I mean? So this can happen. There can be at most one oriented edge coming from a vertex, but two can point towards a common, but at most two can point towards a common vertex. So the rules, over here for the secondary structure, less than or equal to 1 from outgoing, and less than or equal to 2 incoming at each vertex, and by the way, there's a separation